Hello, my name is Dima Kitavenka, and I'm a PhD student at the Computer Vision Learning Group of Professor Björn Omer at the Ludwig Maximilian University of Munich. In this paper, we propose a novel approach to training embedding functions for deep metric learning. Conventional approaches to DML compute image embeddings independently. We design a novel mechanism for conditional image embeddings. This means that the embedding of the query image depends on the image we compare it to. We achieve this by adjusting features of the query image using the representation of the second image through a cross-attention block. Specifically, we compute a tension between the spatial features of the first image, used as keys and values, and the holistic embedding of the second image, used as queries. This simple switch to conditional image embeddings allows for training stronger DML models that outperform state-of-the-art results, while having no negative impact on inference speed. The main task of representation learning is to find a good embedding function that maps similar images close together in space and different images far apart. Typically, this is accomplished by mapping images one by one to a common embedding space and comparing their embeddings with each other. In this example, distinctive parts may include the shape of the armchair or the texture of the leather. However, when humans compare query images, they tend to focus on different parts of the image depending on the image being compared to. If we compare those two images jointly, it seems reasonable to look at the chair leg or the background region. Thus, instead of embedding images separately, we need to fuse information from the images being compared and learn conditional image embeddings. How can we obtain a conditional embedding function? By starting with a conventional approach of fitting the image to the encoder network E and the projection function phi. We await local parts of one image with a holistic embedding of another image. Those parts are highlighted with red frames. We implement this idea using an attention mechanism. We compute cross-attention between the spatial features of the first image, taken as keys and values, and the holistic embedding of the second image, used as queries. This results in the first conditional embedding. Now, we can repeat this process multiple times to increase our chances of extracting good features. In this way, we obtain a hierarchy of conditional embeddings. Finally, we use the final conditional embedding to compute conditional similarities. These similarities are then fed into the neural network and used to compute the loss and train the model. We noticed that in practice, using the initial embedding phi0 is sufficient to achieve high retrieval scores. This indicates that our approach primarily improves the training signal and facilitates the learning of better features. Additionally, from the model architecture, viewer can see that our approach mitigates the lossy compression of the signal in the pooling layer. This is a negative effect that all approaches using convolutional backbones suffer from. Our model architecture utilizes multiple cross-attention layers to bridge the gap between the original unconditional embedding and the final similarity, and allow backpropagation to update encodings more directly than through a lossy pooling layer. We evaluate our model using the widely used metrics. We call it K and NMI scores. Both measure retrieval performance. Our approach improves over holistic embedding-based state-of-the-art approaches by at least 4.3% on the CUV dataset, 1.7% on cars, and 0.9% on SLP. This clearly demonstrates the importance of emphasizing local features, conditioned on the holistic representation of another image. Retrieval performance depends on the number of cross-attention blocks in the model architecture. Moreover, for a model with n cross-attention blocks, we obtain similarities at different levels, and each of those can be used to compute retrieval scores at testing phase. This figure summarizes recall-at-once scores on the test sets of the cars and CUV datasets. We observe improvements in performance when using multiple cross-attention blocks, but this improvement saturates around 6 blocks. We also see that using higher similarities as n for inference degrades the performance, thus indicating that during the test phase it is reasonable to use initial similarity as 0. That means that unconditional embeddings phi0 already outperform other state-of-the-art models. Here, we visualize the attention maps of different cross-attention blocks for two exemplary image triples. For each triple, we compute the attention maps between the middle image and each of the images at the top and at the bottom, and these attentions are visualized in the top and bottom rows respectively. Different columns stand for different cross-attention blocks. We visualize here on the layers 2, 4, and 6. In the middle row, we show the difference between the upper and the lower row to amplify locations with different attention. We observe that later cross-attention blocks focus less on the background clutter and more on distinctive features of a bird. All birds on the left image share the same breast color, hence the attention is focused more around the head area, which is helpful to distinguish anchor image in the middle from the top image. In the second triple on the right, attention is concentrated around the headlight area. This is the only shared area between the anchor image in the middle and the top image. To summarize, in this work, we introduced the concept of conditional embeddings. The representation of one image in the tuple is learned conditioned on its partner, making it significantly easier to focus on meaningful features for this particular comparison. This results in high retrieval scores on all three main datasets common for deep metric learning. We have further extended this concept to the hierarchy of conditional embeddings that gradually incorporates information about the tuple into the original and conditional embedding. Our approach only augments DML during training and introduces negligible computational overhead. Moreover, there are no changes to the deep metric learning architecture during the inference stage.